Okay, good morning students. As you know, my name is Subodh Pandey and you are floating in the world of physics. We are going through a chapter and the chapter name, or we can say the unit. We are going through a unit and unit name is the optics. That unit is divided into two parts. One part is your ray optics, other part is your wave optics. Okay. So in the ray optics, there is a last chapter and the chapter name is your optical instruments. In the optical instrument, the last topic is astronomical telescope. So in this lecture we will discuss about each and everything. What is astronomical telescope, how we can form it, what are the basic ideas behind the formation, and what is its use. So let's get started. Here you can see that the telescope is used to view the objects which are far away from the earth, or we can see the heavenly bodies. Okay, so heavenly bodies can be seen by using the telescope. Now as you can see here in this diagram, there are two lenses are used. First is your objective lens, whereas the other is your eye lens. So objective lens is what? Objective lens is basically, we can say that the objective lens. Okay, so objective lens, this is your objective lens, and it is we can say that towards the object side. Okay, so one lens is there which is object side and the name is objective lens. Okay, and the other lens we can simply say that the second lens, that is your eye lens. And eye lens, we can say that we get the final image. Okay, so the lens from which we get the final image is the eye lens. As you can see here in the diagram, this is your objective lens which is of larger aperture. Other lens is your eye lens which is of smaller aperture. Now the question is, why we are using the objective lens for large aperture and why are using the eye lens comparatively to a small aperture? The reason is quite easy, that objective lens has large aperture, and this is due to, or we can say so that maximum light, okay, maximum light coming from the object, coming from the object can enter through it. Okay, and if the aperture is small, so the light whatever is coming from the object will be minimum. But if we kept the aperture large, then the maximum light can enter, or we can say pass through the objective lens. And why we are in need of the large aperture? And the reason is quite easy, because if the maximum light coming from the object, so the final image will be clear and bright. Okay, and this is because we want clear and bright image, clear and bright image. Okay, so because we want clear image, that's why we want maximum light from the object, and for that we make the aperture of the objective lens large. Okay, so or we can say I want to show you that what is the basic sense of large aperture. Let's see. If we draw a diagram like this way, we can simply say that if your lens, one lens is like this way, okay, and the other lens, we can simply say that your other lens is like this way, and your one another lens is like this way. So if we are taking here three lenses, as you can see, this is your first lens. Let's suppose this is your second lens, this is your third lens. So the aperture of the third lens is greater than the aperture of the second lens, greater than aperture of the first lens. So I hope that you can now better understand what is the basic sense of the aperture. So aperture is the effective part of a lens which actively participates in the phenomena of the refraction. Okay. So the maximum light passes through the lens, it means the maximum area is participating in the phenomena of refraction, it means the maximum aperture is there. If the less light is passing through it, it means the less area is participating in the phenomena, and the aperture will be less. So objective lens must be of large aperture. This is your first concept. I hope and I believe that it is clear. Now we will discuss about the second point. What is the second point? As we know that if the object is at infinity, this says let be infinity. So if the object is at infinity, then the rays are which are coming from the object are parallel to each other. Then what is needed that we are not showing here the parallel rays parallel to the principal axis. What does it mean? What I am trying to explain you, I am trying to explain you that if let's suppose that your lens is there, let be this is your lens, okay, and we can simply say that we have a axis here also, principal axis, like this way, let be this is your principal axis. Then we can also represent the rays which are coming from the object like this way. This is the rays which are parallel with the principal axis, and this ray is also parallel with the principal axis. It means these two rays are coming, we can say coming from the object which is at infinity, okay, and after refraction these two rays passes from the point of focus of the lens. So it will be the point of focus of the lens. Okay, so if we take the if we take the rays which are parallel to the principal axis, then what we get a point image. So this is basically a point image, and if we get a point image, then how is it possible to magnify a point? Or we can say that a point can be magnified but not up to a definite length. Okay, so we are in need of that. Whatever image we are getting from the parallel rays, that must have some definite length, and for that actually we can say that we have taken a lens like this way, okay, and this is your lens, and then the principal axis, this be your principal axis like this way, okay, and the rays which are coming, that are first ray is coming like this way. You can simply say that this is your first ray, and this is the second ray which is also parallel. This is your second ray which passes through the optical center, and the ray, you can also this ray strike and falls, finally passes from the focus like this way, okay. And here you can simply say that we get a point of intersection, and this is your image A dash and B dash. So I hope and I believe that now the criteria is clear, that why we are not choosing the rays parallel with the principal axis but parallel to itself. Means we are not considering this diagram for the objective lens, but we prefer this diagram for the objective lens. You can see here this one. Okay, so why we are not choosing this diagram, we are not taking the rays parallel with the principal axis, because we get a point image, and point image is very difficult to magnified. That's why we are taking rays which are not parallel to the principal axis, so that we get some definite, this is your definite height of image of the object, and this can be easily magnified. So this is the second point that you should remember here. So first point is what? First point is that your objective lens must be of large aperture. Second point, whatever rays are coming from the object, that must be parallel to each other but not parallel to the principal axis. So these 2 points is now clear to all of you. Okay, now what? As I have explained to you that when the parallel rays comes, then they meet at the point of focus. It means this will be your point of focus, or we can say FO, objective lens, or we can say the focus of the objective lens. Okay, so here this is point to FO, focus of the objective lens, and A dash B dash is the image, or we can say the definite sized image of the object. Now whatever the image is formed by the objective lens, that behave like an object of the eye lens. So we will again draw the ray diagram. As you can see that now forget the objective lens or the rays which belongs to the objective lens, just focus on your image A dash B dash, and focus on the lens I lens. So one ray which is parallel to the principal axis passes through the focus of the eye lens, and the other ray passes from the optical center O dash of the eye lens. And as we can see here that the separation is increasing. So when we pull these rays back, then they intersect at a point, and we get the final image A double dash B double dash. So this is your final image, or the image what we get from the eye lens. Okay, so I hope and I believe that up to here each and everything is clear to all of you. Now what we have to do, we have to find out the magnification. So firstly we have to write the magnification, and magnification that is represented by small m, and the formula is your tan beta upon tan alpha. Beta is what? Beta is the angle with image, okay, and alpha is angle with your object. So this is your basic diagram. You can see here this is your object, so this be your angle alpha, and this be your angle beta. Now we will focus on the two lenses and the intermediate image here. Then what will we get? Let be this is your roughly diagram. Okay, this is your one lens, this is your another lens, this is your principal axis, and this is your, we can say that intermediate image A dash B dash. This is point your O, this point is your O dash. You can see clearly in this diagram. Okay, So this is objective lens, I lens, O dash and A dash, B dash, which is at point FO. So this be your point FO. Okay. Now as you can see that here is a ray you can see in that particular diagram, and this angle is taken as alpha. Let see here, this is angle alpha, so the opposite angle must be alpha, so this angle will also be alpha. Okay, so here we can directly write that this will be alpha, and one ray is like this way you can see, and the angle is here beta. So you can compare with your diagram, proper diagram. This is your angle beta. Okay, so here you can see that this is alpha and this is your beta. Okay, now if we consider your triangle here, and the triangle may be your taken as A dash, B dash, O, and we calculate the value of tan alpha. So tan alpha is your perpendicular, means A dash B dash upon base. Base is your OB dash, and if we calculate tan beta from the triangle taken as A dash B dash and O dash, this is your O dash. Okay, so again this will be perpendicular A dash B dash upon base, that is O dash B dash. So this is your final expression for the magnification, and these values are calculated by the diagram whatever we have drawn. Okay, now put the value of tan alpha and tan beta in the above formula. Then what will we get? We get m, that is your tan beta upon tan alpha, and tan beta is your A dash B dash upon O dash B dash, and divided by tan alpha, that is A dash B dash upon OB dash. Okay, you can see here this is tan alpha and this is your tan beta. Okay, now as you know that these two are multiplied, then the value of small m, what we get, that will be OB dash divided by O dash B dash. Now look at the diagram. What is OB dash? So where is your diagram? This is OB dash. OB dash, that is nothing but your FO, focal length. So it can be written as FO. Okay, and O dash B dash. So as you can see here, O dash and B dash, as I have told you that the image whatever is getting from the objective lens behave like the object. It means this is the object distance, or we can say represented by UE. Okay, so here now we put the value, that will be minus UE according to sign convention. So OB dash, that is your plus FO, or we can say the focal length, but the O dash B dash, that is the object for the eye lens, that's why it is written as UE. So this is the value of M. Now what? Apply the lens formula for eye lens. For eye lens we can write that lens formula 1 upon f equal 1 upon v minus 1 upon u, because it is for eye lens, so E and E and E. Okay, now as you can see that the value of m, that is FO upon UE, it means this is 1 upon UE, so multiply by FO, so we get FO over FE, FO over VE plus and FO over minus UE. I hope you are getting what I am doing here. The value of M we are searching, that is FO upon minus UE, so FO upon minus UE, that will be M. So that will be FO upon FE, and that will be FO upon VE, that will be M, and we have to find out the value of M. So what we do, we can calculate the value of m. So m will be, as you can see here, FO upon FE. So FO upon FE minus, and this will be FO upon VE. So FO upon VE. Now what? If we take FO upon FE common, so FO upon FE, if it is common, then it will be 1 minus FO upon FE is divided by FO upon FE, that will be 1 minus, and now FO upon VE and divided by FO upon FE, so it will be FE upon VE, so it will be FE upon VE. I hope that this step is also clear to all of you. Okay, now firstly we will rough it, and then what we can write here. Basically this is your final formula, but here one thing you have to remember, that what we have to remember, that as I have told you, that the final image what we get, that will be add to the distance of distinct vision for the normal eye. It means the value of VE will be capital D. Okay, now put the value V equal capital D, and we get the final value, that is FO upon FE, that is will be 1, and minus FE divided by D, or according to sign convention here will be minus D, so it will be plus D. Okay, so this is your final result, or we can say the final answer for the magnification of the astronomical telescope. I hope and I believe that up to here each and everything is clear to all of you. Now you can assume some more basic adjustment in this derivation. What are the basic adjustment? As you can see in the diagram, where is the diagram? The main diagram, this one. Okay, if we suppose that the FO point is very close to eye lens. Okay, if FO is very close to eye lens, then what will happen? If FO is very close to eye lens, then what will happen? Then FO will converted into the distance between these two lenses, or we can say the length of the telescope. Okay, so in that situation, or we can say in that condition, in place of FO we can write capital L. Okay, so this is the, we can say that assumption that if FO is close to the eye lens, then only you can place the value of FO, that is equal to your the length of the astronomical telescope. So I hope and I believe that this lecture is quite easy to understand to all of you. This is your question which is based on the astronomical telescope. Now we will see what is given in the question. As you can see that it is clear mentioned here that you have an astronomical telescope, but what we are getting here, that are the focal length of objective lens. So focal length of objective lens, that is given by FO, or we can say written by FO, and 200 centimeter. Also eyepiece has also focal length, so eyepiece, that will be FE, and it is 4 centimeter. The telescope is focused to see an object of 10 km from the objective. It means 10 km. You can see that the focal length is in centimeter, but the distance of the object is in kilometer. It means you can consider that the object which is kept in front of the objective lens, that is nearly infinity. Because if we compare the centimeter centimeter to kilometer, then you can imagine that it is nearly about infinity with respect to the centimeter. Okay. And also the condition is that the final image is also at infinity, what final image VE, and that is also at infinity. So in astronomical telescope, this condition is obvious. We know that the object is at infinity, but for image we have two conditions here. As you can see that first condition, that we at your minus d, or we can say the distance of distinct vision, or we can say that 25 centimeter. And the other situation on which this question is based on, that the final image is at infinity. In that condition, what we have to do, we have to one again just look at the final expression what we are getting here, that is m equal fo upon fe 1 plus fe upon d. So in that condition, in that situation, this term, or we can say fe over d, becomes minus 1, and not we can say minus 1, that can be neglected. Okay, only 1 will be there. And why we neglect this term? Why we neglect this term? Just neglect the term. This you can see in your simple microscope. Simple microscope. So in simple microscope, you can easily see that when the final image is at infinity, then F over D can be neglected. Okay. And the final expression can be converted as FO upon FE, FO upon FE, or we can say with sign convention minus FO upon FE. Now place the value of FO, the value of FO, that is 200, and the value of FE, that is 4, so it will be minus 15. So here it is given that to find the length of the tube and the angular magnification. So angular magnification is your minus 50. Okay, and the length of the tube, as I have already told you that in your diagram, this one is your proper diagram, and in this diagram I have told you that if we consider that FO is close to the of the optical center of the eye lens, it means FO is nearly equal to O dash, then L become FO. So in that condition, or from that concept, we can say that length, and that will be the focal length. So the length will be 200 centimeter. So this question and the assumption behind the formation of the final image at infinity is clear now. So I hope and I believe that this question, this derivation, and each and every concept behind the derivation is now clear to all of you. Okay. So now what you have to do, you have to note it down in your notebook firstly, then try to remember each and everything what I have explained to you. Then number 3, what you have to do, you have to try the derivation by yourself. And number 4, it is obvious that you have to try the numericals based on astronomical telescope. Okay, so thanks for watching me, thanks for listening me, and best of luck.